In this video, we're going to look at a way of representing the set of complex numbers geometrically. You'll recall that each complex number is associated with two real numbers, the real part of the complex number z and the imaginary part of the complex number z. So these real and imaginary parts are both real numbers, a pair of real numbers. Now we do have a method of representing pairs of real numbers, and it's called the Cartesian diagram, or the XY plane. So the pair of complex numbers, for instance, if we were looking at z in particular being 3 plus 2i, the point 3, 2, we plot 3 along the x-axis, 2 up the y-axis. So we can do this and plot the point z, complex number 3 plus 2i, in precisely the same place. And if we do that, we're using this diagram to represent individual single complex numbers. So this point here would represent the one complex number 3 plus 2i. So we now have what we'd have to call the real axis, which has the real part of the complex number in it, along it, and this we would have to call the imaginary axis. And just as 1 is the real unit along this real axis, I is the imaginary unit, which is placed 1 unit up this, what used to be called the y-axis. Still can call it the y-axis and the x-axis, but usually called the real axis and imaginary axis. So there is the point z sitting there. We can also think of it as being associated with a vector, a position vector, one that's tied to the origin and goes out to this point, which represents the complex number 3 plus 2i. So one point representing the number, and it's associated also with this position vector. Now, when the Cartesian diagram is used in this manner to represent complex numbers, it's not called the Cartesian diagram anymore. It's called the complex plane, or the z-plane. It's also called the Argand diagram, after Jean-Robert Argand, who discovered it in 1806. Now, there was someone called Caspar Wessel, a Norwegian surveyor, who discovered it in 1797. So, by all that's reasonable, Caspar Wessel should have his name attached to this, and it should be called the Wessel diagram. But by the quirks of historical quirks, he's not remembered for this, because he published it in a very obscure journal, Norwegian journal. Nobody paid any attention to it. So it's got Argand's name attached to it, Argand diagram. It was also discovered independently in 1828 by John Warren, and also by the famous Gauss in 1831. But anyway, here's the complex plane. Now, let's do an example using this, and we'll use the complex number 2 plus 3i. There it is. And we want to look, first of all, at the negative of that complex number. Now you know the negative of 2 plus 3i would be negative 2 minus 3i. It's the complex number that adds to 2 plus 3i to give you 0. It's the additive inverse of z. Where is it in this diagram? There it is. There's the vector associated with that complex number, and there's the vector associated with its negative. One way to think about this is that we take this position vector of z and rotate it by a half turn, 180 degrees, or pi radians. So sending a complex number to its additive inverse, to the negative of z, is equivalent to a half turn about the origin. So there's an operation on a complex number resulting in a geometrical transformation. Half turn. Let's now look at the complex conjugate of 2 plus 3i, and we know that's 2 minus 3i. The real part remains the same. The imaginary part, you change signs. Where is it in the diagram? Here it is down here. There's z bar. And you'll notice that what we've done this time is reflected that point which corresponds to z in the real axis. So once again, an operation on complex numbers has resulted in a geometrical transformation, this time reflection in the real axis. So worth emphasizing that calculations or operations to do with complex numbers can be interpreted using this Argand diagram as geometry or geometrical transformations. Let's move on and have a look at addition. And to illustrate this, let's take two complex numbers. The first one's 1 plus 4i. The second one is 2 plus I. You might like to try this before I show you the result. So you see where z1 plus z2 is on this diagram and what the geometry associated with that is. So stop the video and explore the sum of these two vectors. Okay, so let's have a look at that. Let's plot z1 and plot z2. Let's put in the corresponding vectors that are associated with these two complex numbers. Position vectors starting at the origin. There they are. Now we know to add z1 and z2, we first of all add the two real parts, 1 plus 2 is 3, and then we add the two imaginary parts, 4 plus 1. Very similar to vector addition. If we think of the vector 1, 4 added to the vector 2, 1, we'll end up with 3, 5 as a vector. 3, 5. So this point up here, z1 plus z2. And in terms of the geometry, we're doing the vector associated with z2, vector associated with z1, 1, 4, followed by the vector associated with z2, that's 2 plus I, and the resulting vector associated with the sum is the diagonal of this parallelogram that's appeared. So it's the parallelogram law for the addition of vectors that's appearing when we add these two complex numbers. Let's have a look now at the difference of z1 and z2. A similar sort of thing is going on where we've got 1, 4 minus 2, 1, which would leave us with minus 1, 3. That's the vector analysis of the situation. Just doing the calculation with these complex numbers, the real part's 1 minus 2 is negative 1, the imaginary part's 4 minus 1 is 3. So we get the complex number minus 1 plus 3i. That's up here. Minus, there's z1 minus z2. And in terms of the geometry, there's z1 minus z2. We have now to, if you like, add, think of it as the adding of the negative of z2. There's negative z2. Remember that was got by a half turn about the origin of pi radians. So there's minus z2, and then to add z1 followed by z2, 2 along 1 down, there's the parallelogram that we get from adding z1 and negative z2, and its diagonal would be the vector associated with the resulting complex number z1 minus z2. So there's another parallelogram appearing. And you'll note that in this original one, where the sides had vectors representing z1 and z2, that the one of the diagonals represents z1 plus z2. The other diagonal, the shorter one in this case, is representing z1 minus z2. Of course, it's not pinned to the origin. We have to move that vector to the origin to find the position of the point representing z1 minus z2. But interesting that both these diagonals involve the sum and the difference of the two complex numbers. So a lot of good, meaty, interesting geometry coming from this way of representing complex numbers when we look at addition and subtraction. So I think now it's time for you to have a shot at a question. So let's look at the following, and I want you to consider the complex number 1 minus 2i, call that z1, and the complex number negative 3 plus I. And first of all, I'd like you to plot z1, z2, minus z1, minus z2, z1 plus z2, and z1 minus z2. So stop the video and try that yourself. Make up a diagram and do this. Okay, let's try this then. 1 minus 2i, z1. There's its associated vector. z2, and there's its associated vector. Minus z1, can be obtained half turn around the origin from this vector to that one. So that's minus z1. Minus z2, there's z2, so half turn about the origin. There's minus z2. So incidentally, minus Z1 is minus 1 plus 2i, minus Z2 is 3 minus I. We just need to read them off after we've done the geometry. Z1 plus Z2, there's Z1, there's Z2, so Z1 followed by Z2, and there's our parallelogram appearing. There will be the vector associated with the point representing Z1 plus Z2, minus 2 minus I. And Z1 minus Z2, there's Z1, there's minus Z2, so Z1 followed by the minus Z2, there's the parallelogram again, there's the diagonal vector representing the vector representing the complex number Z1 minus Z2, and we can read it off, it's 4 minus 3i. So I hope you managed that. Let's try one more before we sign off in this video. In this one, let's just use exactly the same vectors as we had before. Minus 3 plus I. But this time on the diagram, there's a different diagram this time. Z1, Z2, the conjugate of Z1, the conjugate of Z2. Again, we'll put in the sum of Z1 and Z2, but also this time the conjugate of Z1 plus Z2. So go ahead and stop the video and try to plot the points, the associated vectors of these two and the various combinations. Okay, let's see how you got on. So Z1 again, 1 minus 2i, there it is, with its associated vector. Z2 is minus 3 plus I, with its associated vector. Z bar, Z1 bar, remember we said that's reflection in the real axis, so it'll be up there, and there's its associated vector. So Z1 bar is 1 plus 2i. For Z2 bar, reflection in the x-axis and the real axis would take us down to there, so there's Z2 bar, minus 3 minus I, and that's its associated vector. Now let's have a look at Z1 plus Z2. Maybe we should do this one in green. So there's Z1 and there's Z2. The addition of Z1 and Z2 is Z1 plus Z2, and there's the resulting parallelogram. So Z1 plus Z2, there's the associated vector, and we're talking about minus 2 minus I. And in red, let's have a look at its conjugate. So that would be up here, the conjugate of Z1 plus Z2, just sitting there. Now, it'd be interesting to note that Z2 bar and Z1 bar are sitting in a parallelogram with Z1 plus Z2 bar. This would imply that when you add Z1 bar and Z2 bar, we'll get not only Z1 bar plus Z2 bar, this will turn out to be identical to Z1 plus Z2 bar, the conjugate of the sum, is the sum of these two conjugates. Now, this is something that we saw previously when we looked in the video on conjugate surds. We worked this property out. So it's nice to see that type of result appearing in the geometry on this Argand diagram.